So in this lecture, we're going to talk about digital logic design. And in this class, you're going to use digital logic design for labs 2 and 3, but it's also good to know something about digital logic design so you can appreciate what goes on in actually building the computer. So what are we going to talk about now? We're going to talk about first combinational logic. This is how do you put logic gates together. And we're going to start out going from logic to truth tables, and then we're going to go the other way around, from truth tables to gates. So that's using Carnot maps. We're going to talk about some common components that you see in logic design, in particular multiplexers, encoders, and decoders. After we've talked about that, we're going to talk about sequential elements. So we're going to do that by motivating it with an example about how you build a counter. We're going to go into details of how memories and latches are built, and sort of pull this all together saying how do you design logic systems. So material that I'm not going to cover, finite state machines. This is Appendix C, Section 10 in the book. So to get started, here are the basic logic gates we have. Now, if you look at this list, most of these you're familiar with. These ones up here you should be very familiar with. I expect everybody knows what an inverter is. It does not A, it reverses the signal, or AND or. And the notation over here should be fairly standard too. So for AND we have A times B, that's A and B, and for OR we have A plus B, A or B. And then we have other gates which you're probably less familiar, but you've probably heard of them. So here's NOR, this is not OR, so not A or B, and NAND, and XOR, and XNOR. So these are the basic building blocks for all the logic design. Now to understand what these gates do, we look at their truth tables. And what the truth table does is it defines the behavior of the gate, that is its output, as a function of its inputs. So if you look at the table here, there are 3 columns. It's one column for one of the inputs, another column for the other input, and finally a last column for the output of the gate. And you can see that this behavior does exactly what we expect. The output here is only 1 when both the inputs A and B are 1, which is what you expect from an AND gate. So this truth table defines the behavior of the gate. It defines its output for all possible input combinations. So we can look at a bunch of the other truth tables here. So this defines all the gates we had on the previous slide, and you can see they do basically what you'd expect. Here's OR. So the output is 1 if A or B are true. Now let's take a look at some logic equations and see how you can figure out what they are from their gates. So here's an equation, A or 1, and I'm telling you it equals 1. So let's work this out from the truth table. So here's the truth table for OR, and what I've done is I've highlighted the places where the input B is 1, so we're the equivalent of A or 1. And what you see here is that if A is 0 and B is 1, so that's 0 or 1, we get 1, and 1 or 1 also gives us 1. So this does show us that A or 1 is 1. We can do the same thing for A and 1, but here we get A. And again, here's the truth table for A, for AND. We see 0 and 1 is 0, and 1 and 1 is 1, so therefore A and 1 is just going to give us A. We can do following for A or 0, which is going to give us A. We can walk through the truth table and see the same thing here. And then finally for A and 0, which is always 0. So no matter what we have for A, if we AND with 0, we always get 0 as our output. There are a whole bunch of other laws for Boolean algebra: identity, inverse, commutative, associative, distributed, etc. You can take a look at these in section C2 of the book. One of the laws that I want to talk a little bit about is De Morgan's law. And that's because it's a fun law to play with, and it's not very intuitive. So De Morgan's law says that not A and B is the same thing as not A or not B. So let's go ahead and prove that this is the case using the truth tables. So here's our truth table. Here are all of our possible input combinations for A and B. And let's start out with AND. So here's the truth table for AND. So we're first going to look at this part of the equation, A and B. And we apply that truth table to our inputs, and here's the result. This is A and B. Now we need to invert it. So now we're going to look at not A and B. So we're going to invert the results we got there, and here's the answer. Here's what not A and B is. Now to see if this equation is true, we need to look at the right-hand side and see how that works out as well. So we'll start out by calculating not A and not B, and those are quite straightforward. We just take our inputs A and B and invert them. And then we're going to do OR. So we can get our truth table for OR, look up what OR does, apply OR to not A and not B, and there's our result. So what you see here is that not A and B is indeed the same as not A or not B. So we've proven that De Morgan's law holds. So to summarize what we've looked at in logic gates, there are a bunch of them. You just need to learn what they do and learn how they behave. Each gate is defined by its truth table. Truth table defines the output for all combinations of the inputs. So obviously if you have more inputs, you're going to have a bigger truth table. And we looked at De Morgan's law, which says that if you have not A and B, it's going to be not A or not B.